Jackson Norris, and take it away.
All right, hello. So this session we'll be talking about galactic inflows and outflows again. And our first speaker is Kat Barger, who will speak about gas flows of the Milky Way and Magellanic clouds.
Greetings, everybody. Okay, so today we're going to be looking at what's happening very, very locally nearby. And here's a quick representation of the Milky Way in the background, and we have the Magellanic clouds in the foreground. We've had a lot of excellent talks that have given us so much wonderful introduction on the CGM. So I'm going to quickly put this in front of you as far as like why it's important. There's a whole bunch of stuff out there. And so these are results from local studies, from COST halos, from other teams. There's a lot of effort. A lot of that effort is in this room today, where what we're finding is that there's a plethora of gas out there surrounding these large galaxies as well as around small galaxies, as Ronman has found with the COST dwarfs study as well. Roughly 80% of the metals reside outside of the disk of galaxies. There seems to be a correlation between what's happening inside the galaxies and what's happening around them as far as the CGMs. They seem to be related to each other and talking to each other. Now, the benefit of studying the CGM really locally is because, like Jess Work said earlier, we would really love it if we can look at this kind of stuff in a mission. And, you know, that's the thing. It's like, if only we could see it in a mission. Well, we can. We just have to go to the Milky Way and the Magellanic clouds right next door in our neighborhood. And so here's a gas distribution of the gas clouds. This is a figure that Josh Peak made that's part of the Mary Putman Review, 2012 review. And what this cartoon has shown you is actually the H1 gas distribution. And so all of the different multicolored confettis is basically showing you a different gas cloud. And so it's all showing you H1, and it's based off of their actual distances and morphologies and all those good things. And so one of the things that this figure is not showing you is where all the ionized gas is. And so there's a plethora of ionized gas. We find that most of these gas clouds are at least 50% ionized, if not more. Okay, so where is all this gas coming from? One thing I want to point out, though, real quick before we go into that, is that if you look over here, this high-velocity cloud population, which is essentially gas clouds that are moving with motions that are inconsistent with galactic rotation. If you look over there, I want to point out that these gas clouds are 15 kiloparsecs or closer to the disk. And so this stuff is really, really close by. And I want to emphasize that real quickly because, you know, when we look at these absorption line studies, when they have single sight lines through halos, oftentimes they're probing upwards of half a virial radius. Well, remember, half a virial radius for a Milky Way kind of galaxy, that's 150 kiloparsecs. So 150 compared to 15. So that's an order of magnitude difference. So we're kind of looking at slightly different material here, just to point this out. We're looking at the stuff that's much closer to the halo kind of disk interface region. Okay. All right. So the properties of these gas clouds is quite diverse, where if we look at their chemical compositions, they're all over the place. We have stuff that's on the order of a tenth solar, all the way upwards approaching a solar metallicity. And with this diverse range of metallicities means that there's a diverse range of origins. And so let's go through that. Here's a schematic of the general big ideas of where this material comes from. And we're going to start out with the lower metallicity gas first. So that material is going to be material that flows in along the intergalactic medium filaments, which means that it's going to be pretty pristine, containing very few metals. So we're talking about stuff that's on the order of a few percentage solar metallicities. But what I want to remind everyone is that this material has to then flow through the halo of the Milky Way to get to us. And as it's flowing through the halo, it has the opportunity to interact with the halo and the CGM and accrete metals along its path. And so that means that when we look at this gas, it can be metal enriched, and it actually could look like it has much more metals than it would if it was fresh off the filament. And so here's an example of a gas cloud that might have flown in on the intergalactic medium filament. Here we have complex A, and complex A has a subsolar metallicity. Here's the distributions and metallicities here, and you can see that they're a bit all over the place, but they're kind of hovering around a tenth solar metallicity. Remember that it's also going to be very hard for us to measure metallicities when you don't have very many metals, right? Because then you have signal-to-noise issues. But for the most part, it's very subsolar. Now, the reason why I say that it might be associated with intergalactic medium filament, even though it has such a high metallicity is because what we tend to do is when we're able to map out these structures like this, we see their morphology, their distribution, their kinematics. What we do is we try to track back where they came from. We can say, like, could this gas stream be associated with a stellar stream or a dwarf galaxy? Where did this material come from? And when we look in every which direction, we can't find a parent for this gas cloud. We look around, the best we can do is find the orphan stream, and the orphan stream has a similar kind of projection on the sky, but its kinematics are way off. And what I didn't put on here, the distances are actually way off too. And so they're just not the same at all in phase space. And so we can't find a parent for this particular galaxy, this particular gas cloud, which means that it probably didn't come from a galaxy from what we can tell. And in that case, maybe it flew in on the intergalactic medium filament. Okay. Let's go to the next extreme. Material that has really high metallicity. So that's going to be material that is associated with energetic activities in galaxies. We're talking about galactic fountains, galactic winds, this kind of stuff. So with this material, since it's coming out of the Milky Way, we would expect that it would have very high metallicity. So maybe on the low end, maybe 50% solar, but even super solar, so it would have much more metal enriched. And we think that we have an example of that as well with the Smith cloud. The Smith cloud, it has this elongated structure over here, and it has this compressed head over here. Some work that Andy Fox led is that if you look along the length of the cloud over here, we're looking along the wake here, we see very high metallicities. Okay, so these metallicities, we have more than 50% solar. Here's a little bit less. There might be a metallicity gradient. It's hard to tell. There's some beam smearing and kinematic stuff that you have to sort out as far as looking at UV and the H1 and sorting out the Milky Way. But for the most part, we're seeing that this is a very much enriched gas cloud. And so we can ask ourselves, well, what is the origin of this gas cloud? Well, it's too high metallicity to be associated with an intergalactic medium filament, so that's out. There's not a nearby dwarf galaxy that has this high metallicity, except for we have the Magellanic clouds, but those aren't close to the Smith cloud. And so you'd have to think of like, okay, what would the metallicity be of the Magellanic clouds when this material came out and traveling to? It just doesn't quite match up. So then there's idea where it could be flowing out of the disk and cycling through from intergalactic fountain processes, and that seems potentially plausible. There are some caveats without explanation too, is that this particular gas cloud, it's very massive. It has a few million solar masses of material in it. It's quite massive. And so you can't kick this kind of material out with one supernova. So we're talking about processes where you have co-added supernova explosions going off in a disk, like a super bubble kind of scenario. That material gets kicked out, cycles back to the disk, and doing so it gets this cometary structure with a trailing gas behind it, compressed head. And so this is the scenario that seems the most plausible based off of its metallicities. We'll have to sort out a little bit as far as its trajectory and so forth, but this is what matches the best with the metals. Okay. So what's interesting though too is that this particular gas cloud, it lies only 3 kpc below the galactic disk, which means that it's interacting with the halo, and it might already be interacting with the warm ionized medium. And we can see that with this compressed head, and on top of that, we have evidence of interaction over here with this trailing wake region, and on top of this, we have these fragmented offset clouds over here, all telling us that it's interacting with the halo ionizing radiation fields. There's likely Kelvin-Helmholtz, Rayleigh-Taylor instability kind of things going on, which is causing this material to be beat up. Now, the reason why that matters is because this material is dissolving into the halo. And so as it's dissolving into the halo, it's depositing metals into the halo. And once you add more metals, then that means you're able to provide more avenues for the halo gas to cool, condense, and rain back down. So it could help get some of that stagnant material from the halo back to the disk of the Milky Way. So it can help with that kind of cycling process too. Okay, let's look at another extreme scenario. Now, I love looking at the stuff associated with the Milky Way because it's so close by, it's in your face, you can resolve it, you can really see what's going on. But the downside of looking at gas associated with the Milky Way is that you have this inside looking out perspective. And so that really complicates things. But luckily, we have two gas-rich satellite galaxies near us, the Magellanic Clouds, which are also polluting the medium around the Milky Way, which we can study in detail and learn a lot about how these complex processes work in detail because we can actually resolve them. So let's look at the Magellanic Clouds. Okay, so we showed you this slide at the very beginning where we have the large and small Magellanic Clouds here. This is all the tidal debris associated with those galaxies. The large galaxy is 1/100th the mass of the Milky Way. The small one's 1/10th the mass of the large one. We have 50% solar metallicity for the LMC, about 1/5 solar metallicity for the small Magellanic Cloud. And we have debris in every which direction. I don't have a lot of time to talk about all this debris here, but I want to point out that once you add up all that material in neutral and ionized gas, we're talking about on the order of 2 billion solar masses of gas. There's ionized gas that extends 30 degrees off this H1 that you're seeing. This is tracing the H1 gas distribution. And that was done with Andy Fox in 2014 using 69 cost sightlines. So one thing that I want to point out is that when you have galaxies that are interacting with each other, in addition to these tides, you also get the gas inside of them to slosh around. The gas clouds will hit each other, they'll compress, it'll trigger a bunch of star formation activity, and so forth. And so if we look at what's happening inside of the galaxies, specifically the large Magellanic Cloud, we can see that it's very, very bright in H alpha, which tells us that there's likely a lot of star formation activity. So my collaborators, Nicola Lenner and Chris Hauk, they wanted to look at this galaxy for a prospect of having a galactic wind. And so they did that, and they used stars in the LMC itself as background targets, so they would only be sensitive to the material between the stars and us. And they were able to then say, okay, is this material redshifted, blue shifted, and that would correspond to an inflow or an outflow. And so this is the distribution map that they saw, and in every single sightline they looked, there was evidence of material flowing away from the LMC. There's some locations where it's a little bit boring, where you don't see bright H alpha behind it, but yet you still see outflows. So I joined the group, and we wanted to ask ourselves if these outflows, which we think could be related to this recent stellar activity here, we wanted to know if this stellar activity was causing a large-scale galactic wind, or maybe we were tricking ourselves by just looking at tidal debris, because tides could also cause this kind of motion too. And so we really needed to disentangle that. So to disentangle that, what we really needed to do was to peer on the backside of the galaxy, because if it's a tidal process, then you wouldn't necessarily expect it to be exactly symmetric on both sides of the galaxy. But if it was a wind, then you would expect to see similar outflows on both sides with similar kinds of properties. And so nature is sometimes nice and sometimes not too nice, but it gave us one sightline, one AGN sightline that was bright enough to pierce the disk of the LMC to give us a UV bright target that we could probe what was happening in the foreground and background of the galaxy. And on top of that, there is also a disk star, a Wolf-Rayet star, that was right next door. This projected distance right here is 105 parsecs apart from each other, so these two targets are right next to each other. And what that means is because we have an AGN background target and a star, that we were able to probe between us and the star for the foreground, and between us to the disk and to the background from the AGN. Now that's really important because that allows us to break degeneracies as far as velocities and positions with respect to where this material is around the LMC. And here's what we find. Okay, so over here we have the spectra of the star. This is an apparent column density, and we have the spectra of the AGN over here. We're looking at silicon-4 and carbon-4, and here this gray swatch right here, it's representing the kinematic girth of the LMC disk itself. So the stuff that lies on the outside is the material that could be flowing in or flowing out, and I color-coded it for you. So this material over here is blue shifted, and it's approaching us, and remember we're looking towards a disk star over here, so we're only sensitive to the material in front of the galaxy, so that means that this material is blue shifted and it's flowing towards us. It's flowing out of the disk of the LMC. Now we look over here on the red shifted regime, and we don't see any bumps over here, so we don't have any evidence of inflows. We go towards the AGN, And we do see that blue shifted bump, so we have that approaching material towards us. But in addition, we have this red shifted bump over here telling us that we have material flowing on the back side of that galaxy as well. And so this gives us evidence, strong evidence that yes, there is in fact a galactic wind. And we see that the properties, the kinematics are very symmetric, the ionization conditions are very symmetric. It looks like the same thing on both sides, so it's likely the same thing. Now, this material over here, if we look at its kinematics, it's moving at velocities of upwards of plus 150 kilometers a second with respect to the Magellanic Cloud, Large Magellanic Cloud galaxy. So one question we can ask ourselves, well, the galaxy is kicking out this wind, but is this material actually going to escape? Is it going to go anywhere? And with these kind of velocities, yeah, some of it might. We were talking about escape velocities on the order of 115, 125 kilometers a second. So some of it might escape, but possibly not the bulk of the material. But that's kind of not what we see. When we look around the Magellanic Clouds, we do see that there's a high velocity cloud population that has very similar properties that has moved significantly far away from the Magellanic Clouds. And I unfortunately don't have time to show that right now. But instead, I'm going to show you another process that can help assist the winds come out of galaxies in the case of interacting galaxy pairs. And so this brings me to the Magellanic Stream. So here we have the LMC, SMC, the Magellanic Stream region, the leading gas over here. And I want to draw your attention right over here where we have this little gap. And that little gap, if we zoom in, Mary Putman thought that that might actually be indicative of two actual filaments in the stream, that there might be two gaseous filaments. And so David Nidover, he looked at the stream and he looked to see kinematically if in fact there were two filaments, where now we have the LMC, SMC, here's their velocity component, and here's essentially angular distance from the LMC. And when he did that, we have here the stream region. He did find that there were two coherent filaments kinematically, one tracing back to the bridge region, the region connecting the SMC and LMC, and he found that there was another filament tracing back to that 30 Doradus region. Annie Fox and Philip Richter, they got together and they did a chemical evolution analysis of this gas, and they found that not only spatially kinematically, but also chemically, these are two distinct filaments. And what's interesting is that we have a metallicity that's on the order of a 10th solar, and another one that's on the order of 50% solar. Now, it's really hard to get tidal material that's 50% solar, because the metals and galaxies are hiding in its gut. That material is locked in, right? It's not susceptible to the tides. And so how do you get metals, such high metallicity tidal filament? And so this is probably kind of like a 1-2 punch kind of thing, where you get the winds kicking the material out, and then once the material is out, well, now it's no longer in the center of the galaxy, and now it can be susceptible to the tidal motions. So it likely got kicked out from the winds, and then it got washed away in the tides, and it flew into this gaseous structure here. So when we look around the Milky Way and the Magellanic Clouds, I want to point out that it's very rich, it's very complicated. We can see what's happening in emission absorption. We can see how its properties, its ionization conditions, densities are changing along the length of all these structures. But they're still very complicated, and there's still much information that we wish we could have, and much interpretation that we could do. And this is when we have just about as much information as we can, and it's still hard to interpret. And so I kind of want to end on a cautionary note that I think that what's happening around galaxies that are a bit farther away with absorption line studies with single sight lines is fantastic stuff, because we're getting some statistical analysis, because here we have a galaxy sample size of 1, but we have to be careful on that interpretation, because if we were to imagine piercing the Milky Way system with only one sight line, it really could look very different depending on which sight line you pierce through. Right? Okay. And with that, thank you.
Any questions? Any questions?
For the silicon-4 lines for the Large Magellanic Clouds,
Yeah.
Through the stars and the AGNs, are they absorption lines, or they are actually a parallel optical depth? It's not working.
these are absorption lines, and it's been converted into apparent column density through a apparent optical depth method. So it looks like emission, but it's absorption. Yeah, it's just been converted already.
Set the tides can then take the gas away. Could that be ram pressure stripping as well?
So there could be a question about whether or not ram pressure stripping can do it. Now the Magellanic clouds lie about 50 kiloparsecs away, 50 to 60 kiloparsecs away, and we think that the density of the halo is probably on the order of times 10 to the negative 4. One of Gertina Besla's students, what was her name, Andy, do you know?
No, no, that's
Okay, well, one of her students was able to look at H1 observations of the disk of the LMC, and she saw that on part of the LMC there was the disk was a little bit compressed, and she made estimates to figure out how dense the halo would have to be in order to reproduce that slightly compressed disk. But it's very low density, times 10 to the negative 4 centimeters cubed. So it's very low density. So ram pressure stripping, it could do stuff, but not at these densities. It'd be minimal.
The wind material is much easier to strip then, right? It's already out of the disk then, out of the LMC a bit.
So ram pressure stripping can affect it more because it's out of the disk, but the densities of the gas that it's interacting with are still very low, and so ram pressure stripping just isn't as strong, so the tidal effects will probably do a lot of it.
Are there any more questions? We have a microphone that works.
This experiment really should be repeated on 3, 4, 5, 6 other AGNs. Are there candidate targets?
No, that's how nature
the only
works.
one?
That's how nature works. They give you that one sight line, right? No, I completely agree. We would really want to see. Now, one thing that we can do, though, so that's towards the disk itself. There are some AGNs off the side of the LMC, and we can do that experiment, and that's the next stage of the project. And when we look, I don't have that slide, but when we look off to the side towards these other AGNs that are just offset, we also do see evidence of blue shifted and red shifted material. Now, I should...
Yeah, I'm happy with off the side.
Yeah.
More coverage.
Now, one thing that I want to point out, though, if you guys don't mind me saying, is that because it's so nearby, we can look at it in both emission and absorption. So I'm part of the Wisconsin H-alpha mapper team, and so I can map the ionized gas out within H-alpha. And so this is the wind in front of the LMC at those velocities, not the backside. I'm doing the backside next. Now, over here, we're looking at the LMC disk itself over here. And this is just the material that would be fast moving compared to the LMC. So it's not the LMC we're looking at here. And actually, these locations show you where the quasars are and the off to the side quasars, and if it's blue shifted or red shifted material that we see. Some of this material right over here that we're looking at in H-alpha might actually be associated with the leading arm, so we have to do a little bit of cleaning up to find out what belongs with what, but we're mapping out this entire thing in H-alpha mission as well.
Okay, we have time for one more question, if there's any more. Go ahead and say it.
The inflow and outflow, can't you see this with H1 maps?
Yeah. I don't have a plot that shows this, but yeah, we do see that there's a high velocity cloud population of material coming out with the H1. Now, with the H1, though, it's tricky because a lot of the surveys only go to, let's say, about 400, 450, kilometers a second in local standard of rest, and so a lot of them aren't getting that backside yet. But now the upcoming surveys are going to go to much higher velocity, so we'll be able to probe that extreme end of the velocity range as well pretty soon. Yeah, so that'll be very interesting.
Okay, let's give Kat one more hand.
Okay.